No hace falta que te vuelva a presentar.
No, it's good. So yeah, we're gonna continue with the discussion on the setting for applying the Allen-Cahn methods to problems with boundary in the style of the Plateau problem. And I want to talk today about what will be the model solution, right? Which should be a half a line. This is the model solution of the boundary. So let's discuss quickly the heuristics briefly. So we can, I want to do a model for a solution that is in R2 minus a point. So the point is the boundary. And I want to find a solution whose nodal set is half a line. So something like this. This is the equivalent of solving a geodesic problem with one boundary. It's not exactly like the Plateau problem. If you want to solve the Plateau problem, then perhaps you will draw something like this: 2 points and then the line, right? Which is like the disk. But when you blow up around the boundary, you obtain an image like this. Right? So this should be the blow up. It's the model solution in that sense. And remember that here we want to find a section whose nodal set is half a line. So this is a section. That's what I would say. It's a section over a bundle, a line bundle in R2 minus 0, which is, like a Mobius bundle around the curves that link with the right? If I take a curve like this, that closes up. I don't want to draw it because I'm messing up the drawing, but maybe I use a different color. So if I follow a curve like this, I should see as my fibers a Mobius band. Okay, that's why I can afford to have just 1 0 along that curve. So the way I propose to, the strategy, one of the analogies, is to look, instead of sections, we can look at odd functions on a double cover, right? But the double cover of R2 minus 0 is the same space. So in this case, if I look at the image of this, there's many functions you can pick. A good one to look at, which I will explain why, is a function that is the set square in the complex way. Right? This has several advantages. It achieves a double cover, but it also stretches things out around the boundary. Right, so that's one stretches this way and shrinks this way. But what will happen in this case is that I will obtain something like this. That's the pre-image of the line. And the pre-image of the circle means if I not the pre-image, but if I lift the circle, of course, the bottom part will also go to the circle. So yeah, this is a good map to use as a double cover because it's differentiable. It's very simple to compute things in this setting. And just to complete the analogy, here what we have is an odd function. Maybe utility 2 minus 0 to R. So how do we construct a solution like this? Maybe before constructing it, I want to say a few things about this projection that I'm quite quick. So properties of phi, this double cover is first, you know, what I said there, sections correspond to odd functions. Like this, just to remind you. But what I'm saying is this analog here. And then if a section, this is perhaps most important, if a section U of the Morris bundle, I'm calling the Morris bundle. Maybe I'll be using a bit implementation here. Over R2 minus the origin satisfies, meaning is critical for the energy, meaning satisfies this equation, you know, locally in the trivialization. Because remember, the Laplacian written as this doesn't really make sense for sections because you need to choose an orientation. But locally, you know, it will satisfy this, and of course, the point is that if U satisfies this equation, minus U also satisfies this equation, so it's well defined. So satisfies this, then you can do a simple computation, you know, that involves the projection to show that U tilde satisfies the following equation. So 4 squared tilde. So it satisfies a similar elliptic equation, but now you can see this either as part of the potential, or you can put it together with the Laplacian, and it's a bit like the epsilon is changing as you go farther along there. And then finally, another important property is, well, this is part, the singularity at 0 at the origin for U tilde is removable. Okay. So that's an important, very helpful fact that you know, here you're solving an equation outside of the origin, but as soon as you translate, because you satisfy this nice elliptic equation, and the functions that we're working are all bounded, so remember that. So you consider sections that are bounded. So if you happen to satisfy this equation, then you can control derivatives and so on and show that the singularity is removed. And then moreover, what is, Steven is going to talk a little bit more about this, but you know, Chandler estimates then imply Chandler estimates for U tilde, which now is an entire solution. There's no problem with the origin. Implies that U itself was a little bit or controlled by x to the 1. So again, U tilde here is a nice function. U, one will expect to see something happening near the origin that looks like a square root. Okay, so that's just some properties of this covering. And you know, now how can you construct the model solution? So to construct the model solution, you can simply use the standard trick of solving the digital problem. Solve the, maybe I make a drawing first. So I have my R2 now. This is the origin, and I'm gonna solve the Dirichlet problem saying this ball with zero boundary condition. So I'm gonna call this ball. So say this is R. So this is BR plus. Let's call it like that. So BR plus R while variable 0. Solve, and then you solve the following equation, which is u tilde r plus magnitude r minus 4 psi square w prime tilde r 0 in the interior. This is a b r plus u r tilde is equal to 0 at the boundary. Okay. You can always solve this because the equation is really nice, right? So an elliptic equation, it has an associated energy, and you just minimize the energy with the boundary condition. So that's a standard trick. And once you do that, you also prove that because of the shape of these.
Why is not only the zero solution?
The zero has too much energy. Yeah, right. Because if you look at the, yeah, that's a good question. So the mark if R is big, then UR plus is in fact positive. UR, sorry, is positive. And the reason is that, so idea, I guess, the energy of 0 is, you know, it's going to be something like, well, the derivative, the Dirichlet part is 0, but you have this, right? Which is larger than any WT or WU. Is the maximum of this function, right? So you can actually argue. I mean, it's an explicit number. That's the simplest way to look at it. So it's explicit, but this is a constant function in all of this, right? So it's growing. Yeah, it's growing like R squared, right? But you can easily produce a function that is growing linearly, because you can make a function that's just 0 along the boundary, and you can, you know, it goes rapidly to 1 or minus 1. So it's going to have 0 energy in the interior, and then all the energy is going to be concentrated along a one-dimensional set. Right, so check that, for example, what should I call it? V, the distance to the boundary. Again, you want to put maybe something like this: the maximum, the minimum between 1 and the distance to from x, so vx or vz, because I'm using this curve, to the boundary of this set, right? Grows. Right. Okay, this is just a computation you can do explicitly. Does it make sense? So clearly, you know, the 0 cannot be the solution because you already have one competitor. And the fact that it's positive, you know, uses these standard arguments that if you're not positive, then you can take the absolute value of the function, so it will touch 0 somewhere in the interior, and that will violate the maximum principle. So that's how you prove this. And similarly, the function is also bounded by 1 because of the maximum principle. It's not difficult to prove. I just want to give you a rough idea, but if you want to know about these steps more, we can talk about it They're very simple. Just need to get used to the techniques. So what's the idea? Then you can take a limit, then define u tilde at x, y as the limit when r goes to infinity of u tilde r of x, y, say for y positive. Right, so I'm literally just taking this limit. And for y negative, this is defined as minus the function. You can even do it in this.
Is the solution increasing in R?
You don't need a minus there, very next.
You don't need a minus, I mean, you don't need a minus, but it's better to put the minus.
Okay.
Because,
You don't need it,
huh?
because you want to be odd.
Yes, exactly. But I think what Jose is saying is that it's also going to be symmetric this way. So you really don't need it, but the correct thing will be to do. Yeah.
Is the solution depending on R, right? Is the solution increasing in R?
Yeah, definitely. Definitely, because it's going to be monotone at every point. Because if you, it's what we were talking
Yeah, the
earlier.
solution is going to be.
Sorry, if you have a solution to an elliptic equation, usually that's positive in a region like this, and you have another domain inside, then this is going to happen. It's going to be on there. Otherwise, you can violate the maximum principle. So this is not true for every semi-linear equation, but in the case of the Allen-Cahn, what happens is whenever you have a solution and you multiply by a constant, positive constant that is less than 1, it becomes a sub-solution. So the proof will be
less than 1, right?
Yeah, of course. So the argument will be something like this. If you have a solution like this, you can multiply by a constant less than 1, it becomes a sub-solution, and then it will eventually touch. And sub-solutions cannot touch that. So that's the idea. Okay, good. So this is the model solution. In the end, you obtain, then you get something that looks like this. It's positive here, it's negative here. But you see, the equation is not homogeneous. You have this set term here. Right? So the way this behaves is that you're gonna have a positive gradient there because of Hoff lemma. The 0 is the maximum of the bar region. So that the Hoff lemma will tell you that the derivative can never be 0. So here the derivative is positive. And then as you go to infinity in either direction, your gradient is going to explode. Right? Because it's a bit like having the epsilon here. You see, this number is becoming really, really large. If I divide by this number, then it's like having a tiny epsilon there. So yeah, you're seeing your solution doing something like that. So another observation is that the nodal sets of these are not going to be planar. There's a few things here that are a bit different than the standard Allen-Cahn, and that difficults the analysis a little bit, because you want to prove something. So for example, is this solution stable? So this is something that we prove. So this was what this was together. Current work with Manuel Delfino and Marco Laman and myself. This shows that U tilde is stable, which is a good thing because you want to use these to invert operators, things like that. But I don't know if it's minimizing. It's minimizing, should be minimizing. So for sure, the projection, which is really the main protagonist that we care about, should be minimizing. I have no hesitation in conjecturing that. But being minimizing here doesn't mean you're minimizing the spares. But I imagine this is also minimizing. So yeah, I haven't thought too hard about that, but the argument is not trivial, or perhaps the argument they use for Allen-Cahn doesn't work directly. Precisely because the level sets are not full entire. Okay, so that's the model solution. Why do I call it the model solution? I think you can imagine that what you use is, what you do is you use this to model the behavior near the boundary for general examples, right? So if we have say the boundary is something like this, you know, and maybe this one a bit there. Sorry, let me just do my second. I'm almost in a circle. Then you have a surface. This, right, with that boundary. Then what you should see, as I explained yesterday, inside you see the one-dimensional model, and at the boundary, you should see the two-dimensional model in play. So here you have 1D, a one-dimensional model, which is the hyperbolic tangent, and here you have the 2D model, which is the boundary. Right. So you have like a field of two-dimensional models around the boundary that are putting together. That's the idea. That's the goal. You want to prove this is the case. So in dimension 3, something else will happen, right? So entire solutions or models. Well, maybe models is not a good name. Yes. So the first one is indeed a model, which is just take the half plane, right? That you would simply obtain by taking a line. So this is one, like something like R. And then on every plane, perpendicular to that line, you put the model solution. Right, so this is, you do a parallel translation of the model solution, and you obtain a new solution, a new section. The other one that perhaps exists that I know, that I think is a nice question, is whether the path and effort exists as a solution of this. So the half and effort would look, I normally draw it like this. I don't know how, I think probably has a better way of doing it. I know what happens near the boundary, and I tell people, you see two planes here and one plane here. Right, and something happens with it. I have a video that I just show Jose, but I have it here to show you, the rest of you. Let's see. So it looks something like this, right? So you can see it. This is a blowdown again. So you can see the two planes coming in. It's a really nice surface that would be really hard to draw. Because it's hard to reflect the behavior at infinity and the behavior at the boundary, because they're very different in a drawing. So you either see one or the other. So yeah, it's a nice surface with boundary. There's a smooth up to the boundary. So it should be possible to construct an entire solution whose nodal sets reflect this. And what should happen there is that the nodal sets should actually drift away faster than the networks do, a little bit faster. Okay, so that's a question, and of course, if it exists, then the question is, what is the inference? What? If it's 1, that's good.
What?
If it's 1, that's good. Because, why is it good?
Yeah.
Oh, because
Why is 1 better than 2? No.
oh no, it's better than 0. Because it's not stable, right?
Mhm.
But this is a stable minimum surface. So, you know, maybe the solution is stable. However, the NFR is not the maximum of 2. So maybe the Allen-Cahn can see an index. So you see Allen-Cahn perturbations, they contain the formations with respect to isotopies, but they can also break the topology.
They can also what?
Break the topology.
Okay.
So because of that, maybe there's an index. Maybe not. Okay, so I want to talk, I think that's it. I want to talk now about the first variation formula for the Allen-Cahn just in general. But do you have any questions about this before we move on? Okay, so I'm just gonna briefly do the computation so that you know, just to illustrate a bit how these techniques work, right? So you know, the energy of the Allen-Cahn is also I'm gonna omit the epsilons because the epsilons is a constant that you can add to the. I'll just put them at the end. So this is the energy of the Allen-Cahn and over a certain region. And being a critical point of this is saying that the first variation of the point u in the direction of a given function is always 0. So this has to be 0 for a phi. And say w1 to 0 or again you can put a smooth space if you're more comfortable. But what is this formula? This formula is you know, you literally just put u plus t phi and take the derivative. So that's the first variation. And the thing is that it's not very geometric. It doesn't really tell you anything about the nouns. So we can write this in a more geometric way, and that's what I want to show you. So the way to do that is by emphasizing the role of a vector when you test your function. So if you so let x be a vector field of sigma, a vector field, and we want to, in an essence, I guess the idea is you can use the isotopies induced by x to change. If you think of the u as a graph, then you can move your domain, and that will change the graph, and that will induce a variation of this. But I'll spare you that part, and I'll say, then consider a variation where phi is of this form, where you have. But this is the same as I was describing. It's the same as using the isotopy. Is the fact of the one parameter family of isotopies in the value of phi. Okay, so you plug that into the equation and see whether you can write this symmetrically. That's the goal. I mean, it's not really that profound what I'm saying, because you see, that is exactly the derivative of u in the direction of x. So if I'm using the isotopies, that's what. Okay, so so you have something like this. have this. Right? Then, as I said, this is gradient. So here is the trick is when you're working with the Allen-Cahn, you're doing these computations, you always have these terms of gradients of u and so on. So the typical thing that you have to remember is that you can write this as the derivative in the direction of this vector of this function. So what I'm saying is like this is a vector field, this is a function. Right? So you can write that. Right? And then for this one I can put these two together. So it'll be something like the gradient of W right? I think that's what I did. Right. So when I continue this, I here get this quantity. This quantity plus 0. So here, what's the goal? I forgot to say that analytically or algebraically. In the first iteration formula for minimum surfaces or for variables, what you usually have is the divergence of the vector field along the surface. Right? That's the first iteration. So here we emphasize the role of a vector field, and we're hoping to see some divergence in the vector field. That should be the most geometric way of expressing this formula. So here, currently, we don't have any derivatives really on x, except maybe this one. So we want to integrate by parts. Okay. So, first, I'm going to tell you about this. So, Mark, let's see if I can remember. I've done this so many times. To calculate this, what was the trick? So, I think I'm going to do this. Right? I want to know what this vector is, another expression. So this is the Hessian of u with respect to these vectors. Okay? So it's symmetric. So I can write this. I can write this as set u. But then this is nice because this is just set differentiating 1/2 of this. Right? Which is the same as the gradient of 1/2 u squared. Right, so then what this shows is that that number there is always this derivative, which I'm going to write just as. No, maybe let's just leave it as this. 1/2 gradient. The good thing is that this is the energy. So when you're integrating by parts, then you make the energy appear. So yeah, that equation, here's all that. I don't know if for anyone it's obvious that this thing is equal to this, but I need to repeat it every and I never remember if there's a 2 or something. If there's a 2 or not. Okay, so then how do we continue? Then now we can replace this because remember when I integrate by parts, so that's essentially what we need. So this is 1/2 gradient of the energy times x. That was the first term, this. And then this one, I'm just going to leave like that. But since we want to understand this in terms of divergences of the surface, notice that this vector is always orthogonal to the surface. Okay? So if I pick if I choose to integrate just on the region, this is different than 0, which I can do because U is a solution of an elliptic equation, and this has measure 0. The set where the gradient is 0 has measure 0. So I can always write it like this. And then instead of writing these vectors, I can write a normal vector. So maybe I call it normal. The derivative in the normal direction of x. But if I'm writing the normal, I'm dividing by the normal. So this is that here. Okay. And then finally, we have the gradient. Yeah, I was going to integrate my parts right away. Okay, so now let's integrate my parts. I'm going to integrate my parts the first term. So I'm going to get 1/2 of this times the divergence of x. Then here I have which I'm just going to leave as it is. There's a 0, right? This is only equal to 0. And then here I can have WU. There's a minus, by the way. No one told me. Integrate by parts. And here there's another minus. So, what can I do here? This divergence is the divergence on the entire space. It's not the divergence on the surface. Right? So, the trick is to do the following. I can take, I can add this entire thing. So, to the other side. So, look down. So, I'm going to say that this is divergence x minus this. Then that's equal, I pass this to the other side, that is equal to this one. Okay. So here what you're seeing is indeed the divergence of x on the sets and another sets times a weight that comes in the energy. And on the other hand, on the other side, what you're seeing is this function, which we call the discrepancy. So this is the discrepancy times the divergence. So this is the first variation formula. So let me explain a little bit what this means. And this, by the way, is all integrals. You create a Do you agree with the formula? You see, this looks now like the first variation of a level.
How did you pass from the second line to the third one again?
From here to here. Yeah. So adding this both sides. Right, so that is this term that appears. And then on this side, on the left side, it cancels with this, but just 1/2. So you have a positive. The rest is just as it is.
Thank you.
So the good thing about this is that you can think of this equation as divergence. It's like an average. So a weighted average. average of first variations of level 6. And this one is what that measure is as a total measure, same quantity. So in essence, what I'm saying is the discrepancy captures how far you are from being minimal. The smallest your discrepancy is, this is true for every vector field, right? X is just a vector field that we're prescribing. So the closer, the smaller the discrepancy is, the closer your level sets are, in an average sense, to being a minimal surface. That's how you should interpret this, or how I'm proposing to interpret it. Okay, and then I could say a few things now about the motonicity formula, which I won't derive, but I will tell you how to derive it. The computation is the same as in the minimal surface case, and you get a similar form. And what I want to discuss with you is what are the differences between the forms. So by taking now x, so you see, first we have a first variation formula for functions. And that was the phi. You differentiate respectively. And we kind of translate it into a first variation formula that is expressed in terms of vector fields to make it more geometric. And now you can repeat the ideas from minimal surfaces. So let's pick the same vector field that you pick when you compute the first variation, the motonicity formula for minimal surfaces by using the first variation. So you take x to be, say, r times that one function times r, where, say, r is the distance to a point. Right? So this is a radial vector field, and multiplying that, or maybe you want to like this. Right, so this is the radial vector field that is 0 at the point, and it grows, as you go to infinity linearly. And this is a function that is going to curve. So it'll be something like this. We have a rho, we have a rho plus delta, and you have a function of 0 here, and it's 1. And then the idea is you plug this into the first variation formula, and then you take the limit when delta goes to 0, and you can, or the derivative of the first variation. So you integrate that, and you take the sorry, I said first variation, I mean motonicity. So let me repeat that. You take this vector field, you plug into the first variation formula, you send delta to 0, and then you obtain the derivative of the motonicity formula. So that's what you get in motonicity formula. So, okay, so let me write down, taking testing x in the first variation formula. And delta to 0, much as in the case of minimal surfaces, one obtains the derivative of the following. So I'm going to write that here. So I'm going to write by E, so let this energy of U in VR to denote the integral of the energy produced in the ball bearing. Okay, so this is analogous to the area. So I'm going to divide by Rn minus 1. We are in Rn as an ambit. And I'm going to subtract. This is what we do. This is the quantity we expect to be monotone. So the monotonicity formula in this case is the following. So it's the integral to R of 1 over tau n. Then there is another integral, beta of W epsilon, which is E beta, and then the entire thing beta. And then finally, we have epsilon b p minus b times 2 of this one, 1 minus I, 1 minus b squared. So, as you can see, I don't really have memorized this formula. It has the main integrals. But let's try to simplify things. So first of all, this quantity you will recognize because in the minimal surface case, what you will have here, remember, is the normal of the minimal surface. But here, of course, it's not exactly the same thing. This integral is happening not on the nodal set, but on the entire space around the nodal set. So it's slightly different. But you can see it again as an average of the same quantity over all surfaces. Okay. So notice, for example, if I divide here by the norm of this, I will have the average coming outside and the normal inside. So again, it's really just like that. But again, this is a good quantity because we want to prove that this is positive. And this here is a bad quantity because I don't know what this is. We'll have to prove that this thing somehow is positive, which is not, by the way, in general. So what I want to point out, though, is that one should really understand this quantity. This is, again, the discrepancy, but if you notice, it has minus the sign. So this is minus the discrepancy. So this is minus the discrepancy. So rather than trying to...
But then you just find that discrepancy without epsilon.
Well, because I chose epsilon to be equal to 1
okay.
here. But yeah, I can always have that. Yeah, so what's the key point here is that in order to have monotonicity, you don't necessarily need to prove that the discrepancy goes to 0, but only that the positive part of the discrepancy is bounded. So you want the discrepancy to be bounded from above by something that goes to 0. You see, because here the negative part is good, because minus times minus will give me something positive. So it's good for monotonicity. So a lot of attention is usually given to that fact, proving that the discrepancy is bounded from above by something that goes to 0. And Stephen is going to talk about this. One of the challenges that we faced when we were doing this at the boundary is that the discrepancy is unbounded near it goes to plus infinity. So one needs to do this a bit more carefully in that case. I should also say, before I finish, that in dimension 1, if you do u prime squared divided by 2 minus w, which is the discrepancy, the derivative of this is 0, because you will have u prime times the equation, which is 0. So for one-dimensional solutions, the discrepancy is a constant. And for the model solution, the discrepancy is 0. So if the discrepancy was 0, that would be great. We just have the multiplicity from. But in general is 1 to be very negative, but sometimes it's positive, and we discover that in this context of the Plateau problem, it's actually unbounded. So one needs to work more carefully. So yeah, I'll stop here and let Steven carry on.
Thank you, Mike. Amazing. Thank you. Stephen, now you are. Are you ready?
I'm ready.
Okay. My camera.
Oh, should have raised, I'm sorry.
Don't worry. Okay, let's start. Yeah, first of all, of course, thanks so much for having us. It's really wonderful to be here with friends and in a place where so much inspiring math has been done. So thanks a lot. Right, Marco hopefully convinced you that getting bounds for the discrepancy is extremely important in this theory. So today I'm going to talk about some of the techniques that are used to actually get these estimates. And as Marco mentioned, the situation is a bit different near the boundary and away from the boundary. First, I'll talk about the interior case away from the boundary. And here, the discrepancy satisfies a nice elliptic equation which can be exploited to get upper bounds using the maximum principle. And this is the content of the Modica gradient estimate. Which I'll present in the situation where I guess the argument takes on its simplest form, which is for a solution on a closed manifold. So we have mg some manifold, and I'm thinking of a solution U to the Allen-Cahn nonlinearity is u cubed minus u. Then the statement is that the discrepancy it's bounded from above by some constant depending on the manifold times epsilon. Okay, so this see the discrepancy. So in particular, as epsilon goes to 0, we have that the positive part of the discrepancy is uniformly converging to 0. Okay. So how do we prove this? We want to compute an equation for the discrepancy. So first of all, we need to figure out what does the Laplacian look like. And using the Blockman formula, we can compute the Laplacian of the first term. So it's going to be grad u in a product with the gradient of the Laplacian. And we have the Hessian term and the Ricci term. Now, if I use the equation, and this first term becomes W prime W squared. And the Ritchie term, I'm just going to bound from below by some constant times gravity squared. Okay, compact manifold, so I can always bound Ritchie above by some K, and then of course this becomes the lower bound. Okay. As for the other term appearing in the discrepancy, if we do the class in W, then we get W prime times the Laplacian plus gravity squared. And did I do a mistake here? Here, we're taking the gradient of W prime. So it's meant to have W prime there. That's going to be important. Here I use the equation again. Is that look good?
Is it not? Why not epsilon, right? Square.
No, fine. No, it's
Is it
fine.
square?
Which one here?
Substitute the equation in.
Yeah, no, that's not a square. I mean the epsilon. Epsilon is on the epsilon.
No, because in the equation we have.
Ah, you have the.
Okay. So putting this all together, we get that the Laplacian of C. Well, let's see. The important thing. Let's just write it out. We're hoping to see some cancellations. So I need to not make a mistake here. Now, this is epsilon. Times the Laplacian of gravity squared minus 1 over epsilon Laplacian of W. So substituting 4. This is the first term. This is the second term. Okay, and now
Bigger than or equal to.
that's right, thank you. Now we're pleased that the first and the final term cancel. And now if you think we want to apply the maximum principle to prove an upper bound of C. So we're happy if the Laplacian of C is not negative. So there are two enemies here. There is this negative term and the term coming from the Ritchie curvature. Okay, so the term involving the Ritchie curvature is easily taken care of. What we're going to do is add in a multiple of u squared. And then this will give us a good grad u squared term, which we can exploit to take care of the Ritchie curve. So I want to add to the discrepancy some constant c, which we choose later, times epsilon times u squared minus 1 over 2. Now, I want to convince you that this term that we've added on is non-positive, right? So on a closed manifold, the solution takes values between 1 and minus 1. And this is easy to see because at a maximum of u squared minus 1, we of course have that the Laplacian is non-positive. This is 2 times u times the Laplacian of u plus 2 grad u squared. Okay, the gradient term I don't need here. And using the equation, this is u times w prime, which I can expand out as u squared times u squared minus 1. Okay, so at a maximum of u squared minus 1, 0 is greater than or equal to u squared minus 1. So what's the conclusion here? Hence, u squared minus 1 is less than or equal to 0 everywhere. Okay, so this term that I added in is non-positive. Good. Now we're working towards looking at a maximal point for this modified function f and getting a contradiction. So let's see what happens at a maximum of f. So we look at a point P where f is maximized, and we assume that this maximum is positive. Right? And what does this tell us? Well, first of all, at the point P, just unpacking the definition of f. Right, since f is positive, we get that grad u squared over 2 is bigger than w minus this term, which we just argued was non-positive. So this whole thing is greater than or equal to 0. In particular, at our maximum, the gradient of u is non-zero. Okay, that's the first thing we need. I'm also going to need to take advantage of the first order condition. Gradient of f is equal to 0. So, what does this tell us? Just expand it out. Marco showed us his mnemonic for remembering what's the gradient of grad u squared. This is the gradient of grad u in direction grad u. And I group the final two terms together as some factor times grad u. Okay, so how do we want to use this? Remember, in the Laplacian for C, there were two enemies, the Ricci term and this W prime term. But now, using the first order condition of the maximum, we have some relation between the hashing of U and W prime. Okay, so I want to rewrite that first order condition in a form such that it's useful for inserting here to defeat this bad term. So how do we do that? If I put this term on the other side and square both sides, then I get this identity. Yep, that looks fine. And because the gradient of u is positive, I can divide both sides by grad u squared. Then this factor on the end cancels. And I can take the grad u inside on the left. So I divide both sides by epsilon, and this looks like this. And you know, this is just the hashing applied to some unit vector. So by the Cauchy-Schwarz inequality, I can bound this from above. The full square norm of the hashing. Okay, which is the term appearing in the Laplacian of C. Okay, now we're ready to put everything together. So the final thing that we know is that the Laplacian of f is non-positive. So this is the Laplacian of C plus C epsilon Laplacian of u squared minus 1 over 2. Okay. Which we already computed above. So, yeah, I don't want to make a mistake on this slide. Yeah. So, we're going to get u times the Laplacian of u plus grad u squared. That's right. Here I've replaced this using the equation. So we get okay, good. Now let's insert the Laplacian of C. Okay, and with this we're almost there. So the good grad u squared that we got from adding in this extra term is exactly what we need to take care of the Ricci term. So that's good. And I want to insert the inequality coming from the first order condition to try and cancel this W prime square. So let's say this is greater than or equal to okay, so this is just inserting the first order condition and regrouping terms. Is everybody with me? Great. So now you see if I expand out this square, the first term will cancel this. And what I'm then left with, well, let's see, I get a minus 2 CU times divided by epsilon. So that pairs with this, and I'm left with minus C over epsilon. W prime U.
No. You're talking about the double, the cross term, true?
Yeah.
I don't know, it's fine.
That's okay. Here we get the final term gives us this.
Would be with C squared.
C squared, thank you. Okay. Now the U squared term, I don't need it, so I'll throw it away. I'll write U times W prime as U squared times U squared minus 1 to make it clear that this is a non-negative term. And now remember, at my maximum, the gradient of U is positive. So by choosing this C to be any number larger than K, we get our contradiction. So this is greater than 0 or C strictly greater than K. Okay. So the function f is non-positive. And if you unpack what that means, that gives us exactly the claimed estimate for the discrepancy, namely that it's bounded by a constant times epsilon.
So the constant value reach comes, right?
That's right. So maybe I'll leave it there for the moment to compare. I've explained to you what to do for a closed manifold, but in many situations, and in particular in our Plateau problem setting, we really need a local version of this estimate. And this is obtained in much the same way, exploiting this good equation for the discrepancy and introducing appropriate cutoff functions and checking that they don't mess up the computation too much. So this I won't bore you with, but I'll tell you the kind of estimate you can get. I think the first instance of a localized version of this estimate is due to Hutchinson's power. The version that I'm about to show you, I mean, Marco and I, we followed the same strategy, but we were able to improve the estimate a bit. So now I just take U to be defined in some ball. Let's say its radius is a large constant lambda times epsilon. Then the solution of the Allen-Cahn equation. Let's give ourselves a bit more space. We'll say this is 2 lambda epsilon. Then the supremum of the discrepancy over the smaller ball of radius lambda epsilon is bounded from above by some constant c times epsilon to the 1 minus q, where this constant c depends on the size of our ball by the constant lambda and on this constant q. Okay, so we can get q arbitrarily close to 0, but at the expense of increasing the constant. So this is not quite as good as what we got in the closed case. And you know, the fact that it's a slightly worse estimate comes from, you know, the fact that you have to introduce a cutoff function. So this is the key estimate for the discrepancy that we need in the interior. Let me talk now a bit about what happens close to the boundary. And we'll do this.
Do you know how depend the constant on lambda? That when lambda goes to infinity, that constant goes to infinity?
Yeah, that's right. No, as lambda goes to 0, the constant
Lambda
goes
goes
to
to 0?
infinity. Yeah,
The constant goes to infinity.
that's right. Because somehow the smaller lambda is, the less space you have for your cutoff function. Now, I want to discuss what happens to the discrepancy in the boundary. And I think the most instructive case to look at is you know, the setting of a disk minus a point. Here, all of the interesting phenomena already arise and are relatively easy to understand. So I'm taking L to be the non-trivial line bundle over some hole in R2 minus the origin, and U is a section solving Allen-Cahn. And Marco explained how to pull this back by the complex square function and get an odd function on the double cover. So this is we want to also work with the pullback here. U tilde is the pullback of U by the complex square. Okay, what is it that I want to say here? We can compute the discrepancy of U in terms of the pullback U tilde. Do this using the chain rule. You find that the discrepancy of U at the point Z squared is the gradient of U tilde at Z divided by 8 times Z squared. Minus W over epsilon. And now already you see that there could be an issue here, because if the gradient of U tilde is not 0 at the origin, then this has to blow up as Z goes to 0. Okay, and that is exactly the problem. Even for the nicest possible solution, the half line, which Marco constructed, the gradient is non-zero at the origin. And the way to see that so for this half-line solution, we know that the zero set is after pulling back, the half-line becomes a line. The solution is positive on one side and negative on the other side. And so just using the Hopf lemma, you know that the zero at the origin, it can't vanish, the function can't vanish the first order there. It has to be non-zero. Okay, so for the half-line solution, we see that the gradient of the pullback is positive at the origin by the Hopf lemma. And therefore, by this computation, the discrepancy of the section downstairs has to be unbounded, close to 0. On the other hand, so we recall that the lift satisfies this nice elliptic. Right, then if U and hence U tilde are bounded, then we expect to get some derivative estimates just using standard elliptic theory. And I'm slightly running out of time, so maybe I'll skip the argument and just tell you what the estimate is. Okay, so there's really nothing to do here except take your standard estimates for the gradient estimate for the Laplacian and substitute everything in. And then what you get is that is bounded by some constant times 1 over epsilon. And all of radius square root of some constant times epsilon, where the constant c depends on lambda and some bound for u. And if we, pass this to the complex square and see what does it tell us about the section u, then what we find is that the gradient of u squared is less than or equal to c over epsilon times 1 over mod z. And this is the ball of radius lambda epsilon. Okay, and this goes back to what Marco said about the asymptotic behavior being like the square root of the distance. That means that the gradient is like 1 over square root, which is exactly what we see here. Okay, so this is a really important piece of this whole theory about the Allen-Cahn sections and the Plateau problems. The fact that by taking a double cover by the complex square and doing elliptic theory upstairs, we at least can control how fast the gradient blows up as you approach the boundary. And I'll stop here, maybe just by pointing out that this of course implies an estimate for the discrepancy. So we get that the discrepancy Z is bounded by, remember in the discrepancy we multiply grad u squared by epsilon. So we get estimate like this. So I'll stop here, and at the beginning of the next talk, I'll show you how combining this estimate near the boundary with the interior estimate, we actually get convergence of the discrepancy to 0 in L1 as epsilon goes to 0. And if you think back to the variation formula and the monotonicity formula that Marco wrote down, it was always an integral of the discrepancy appearing. So that L1 decay is sufficient to get everything running.
Thank you.